Okay, here we go. Introduction to momentum. So momentum refers to kind of the amount of motion that something has. If it's moving and it has mass, it's going to have momentum. And when we talk about its conservation, there's a law of conservation of momentum, meaning when objects interact, the momentum of the objects is conserved, meaning it stays the same. So here we go with, this is a definition of momentum, quantity or amount of motion. And I know that's vague, but we'll get more familiar with it. So I have a little diagram. Here's a bullet, and it looks like the bullet is going fast, but it is also light, meaning not heavy. And then down here we have a bus, and the bus or the van looks like it's moving slow, but it is heavy. So it's possible for these two things, the bullet and the van, to have the same amount of momentum. It's a light object going fast and it's a heavy object going slow. And when we talk about the amount of momentum, it's like the amount of force you'd have to apply over time to slow it down, and the amount of force you'd have to apply over time to slow it down. Obviously, if the van were going as fast as the bullet, it would be much harder to slow down than the bullet because it's heavier. So here's our formula. P is the variable for momentum. M is mass. And V is velocity. So the more massive something is, the more momentum it will have. And the faster it is going, the greater its velocity, the greater the momentum it will have. So let's take a look at units. Velocity is in meters per second. Mass is in kilograms. So a momentum is measured in kilogram meter per second. So you know how the unit of force is a Newton? Well, Newton was, besides a good guy, he was an amazing physicist, mathematician, scientist, so yeah, they named that after him. There isn't a special name for this. You can call them torvils if you like, but the unit of momentum is a kilogram meter per second. So what does this mean? Momentum is conserved. Conserved means stays the same. So let's write that in there. Stays the same. And the momentum of a system will remain the same before and after a collision. Now, look at this word, system. So you, at this point, have probably heard or read closed and isolated system. And we'll talk about what closed and isolated mean. But when we talk about the system, we're talking about, well, whatever objects are involved in the collision. And by collision, we just mean two objects interacting. So they touch and they, move in certain directions before and after that. It doesn't have to be a car crash or whatever. Oh, so for example, here's a car crash. I meant to do that. All right, so here is a car and here's a bus. And it looks like this is what's happening beforehand. The bus is just sitting here parked. It's not moving, has a velocity of 0 meters per second. And here comes the VW bug, and the driver's not really, oh, maybe they're texting. That's bad. So don't text and drive. So a velocity of 10 meters per second, they're not looking where they're going, and they're going to, boom, crash into the back of the bus, excuse me. And we're going to assume that this bus doesn't have the emergency brake on or something, so it's free to roll. So what happens is these two crumple together, and then are going to move off as one. So all of the momentum of the car is now being shared between the car and the bus. So nobody got injured, by the way. So if this is 10 meters per second, the car is going 10 meters per second after the collision, because the momentum, the amount of motion is being shared between the car and the bus, I'm hoping it makes sense that the velocity of both of them together after the collision will be less than 10 meters per second. So they will be moving because the momentum of the car is transferred to the bus as well, but it will be less than 10 meters per second. So how could we calculate that? Well, we say that because momentum is conserved, the momentum before the collision is equal to the momentum after the collision. So we can say the momentum of the car plus the momentum of the, it's a van, excuse me, equals the momentum of the car plus the momentum of the van. And the momentum is mass times velocity, so we're plugging in 500 kilograms, so I made these numbers up. And I should have put them on that other page, sorry. So 500 kilograms is the mass of the car, and then the mass of the van bus is 1,000 kilograms. We were given the velocities on that first page, but I didn't write in the masses, so here they are. So mass of car times velocity of car, mass of van plus or times velocity of van, and this is all before the collision, will equal the mass times velocity plus mass times velocity of the car and van after. Notice how we're using one variable, v, to represent the velocity of both the car and van because they're stuck together, they're going the same speed. So we solve and we end up with this. This is a positive number, meaning they are moving to the right, which it looked like from our diagram. Cool.